This is my intro to time complexity and big O notation. Time complexity quantifies the amount of time an algorithm takes to run as a function of the length or size of its input. Think about it as, how does my runtime change as the size of my input changes? What happens when I double my input size? How does the runtime change? Does it also double? Does it quadruple? And I'm going to teach this through two different functions. The first function is find value, where basically we're given an array, like 1, 2, 3, 4, 5, and we're looking for a value, maybe 78 randomly. We'll return the index of where we find this value in the array. If it's present, we'll return -1 if not. And basically here we just loop through the entire array. If we find the value, we return the index that we found it at. Otherwise, we return -1. How much work do I need to do in the worst case? Well, the worst case is actually right here. It's if the value is 78. It's not in the list at all, right? That means we had to look at every single element in our array before returning. And so how many times did this loop run? It ran however many elements are in the array, or the length of the array. And so I'm going to define n to be equal to the length of the array. And so this loop, in the worst case scenario, ran n times, because that's how long our array is, that's how many elements are in it. In the best case scenario, we're looking for 1. It's not helpful to think about time complexity in the best case, right? Like whenever we were looking for 1 and it just so happened to be the very first element of this list, well, we just got lucky. But that's not what the worst case behavior would be. And so that's not what big O is all about. Okay, so we know that this loop runs in the worst case n times, so we're doing n amounts of work. That means that this function is O of n. You'll hear a lot of people talking about this. They'll be like, this is O of n, this is O of n squared. That's what we mean. Now let's check out the second function. So this function is called pair sum. We return the indices of two values that sum to a target value. So I'm looking for a pair of values that sums up to be 4, and right here I can just say, okay, well 1 plus 3 equals 4. So I would return index 0 and index 2, where these two values are. Okay, so let's actually visualize what this work looks like. So on the first pass, I'm looking at like 1, and I'm comparing 1 to 2, 3, 4, and 5. So it's kind of like 2, 3, 4, and 5. And I'm making all of those comparisons to see if they equal my target value. On the second pass, I start with 2, and then I'm looking at 3, 4, and 5. On my third pass, I'm looking at 3, and then I look at 4 and 5. In my fourth pass, I'm looking at 4, and I'm looking at just 5. In the very end, actually, we don't need to compare 5 to anything, so I'm going to cut this loop short. This kind of looks like a pyramid or a triangle, right? If you look at all of this work that we're doing, like how many comparisons are we doing? It's like we almost have like 4 numbers that we're trying out. How many total pairs do we need to look at? Does anyone know the formula for this? I think it's something like, it's like n times n plus 1, and then this whole thing divided by 2. So 4 plus 1 is 5 times 4 is 20 divided by 2 equals 10. And I think this is right, because this is 4 plus 3 equals 7 plus 2 equals 9 plus 1 equals 10. When we talk about big O, we want to talk about the most dominant term in this function, because really we're concerned with the asymptotic behavior of these functions. So what happens when the input is really, really big? Not this more trivial case where the input is only of length 5, but what if it's 5 million? And so whenever we have really, really big numbers like that, the constants and the lower order terms don't matter. And so if I actually do a little math right here and I factor this out, we get something that's like, let's see if I can even do this, n squared plus n on the top, right? That's the numerator. And then we would divide that by 2. But 2 is just a constant, so we actually just ignore the 2 entirely. So we kind of have this little polynomial right here. And then again, we focus on the highest order term and the most dominant term, so we just ignore this n right there. So the big O of this function is n squared. So we learned about those two functions. One of them, find value, was O of n, and the other one, pair sum, was O of n squared. Cool. So let's actually think about what happens to these as we change the input size in the worst case situation. Well, we know that O of n is linear, and so let's just think about this. If it took 1 second, let's say, to run it when n was equal to 1, what would happen if the size of our input was now 2? Well, it should take 2 seconds to run. And very similarly, for n equals 3, the time will just triple, because if it took 1 second when n was equal to 1, it should take 3 seconds when n is equal to 3. Pretty straightforward. Now let's think about what happens on this side of the equation. Again, when n equals 1, it took 1 second, let's say, to run. But this is behaving in a quadratic fashion, so it's going to grow, the time is going to grow faster than for our linear time complexity. The way that you can think about this is I'm going from 1 to 2, so I'm doubling my input size. But really the way the time is going to work is it's going to be the original time multiplied by the factor that we're multiplying it by, because we're going from 1 to 2. But this is on the order of n squared, so it's going to be 2 to the power of 2, which is 4. So this is actually going to quadruple. So the time will be equal to 4 when we double. Okay, what about when n equals 3? So if we're going from 1 to 3, we are tripling. So I'll take the original 1, it took 1 second, but then we're tripling our input. So it's going to be the factor that we're multiplying our input by, but we got to raise that to the second power because this is quadratic. This is actually 9. So this is going to take 9 seconds. We can learn lots more about time complexity, but thanks for learning with me.